Um, I see somebody raised his hand. Angelina, you can go ahead and please unmute yourself and ask your question. Thank you. So yeah, we can start it. So hello everyone, welcome back to AI Research School Phase 2. Thank you for joining us. I hope you all had a great day today. And today we have Dr. Maliki to give us a presentation on building an object detection with YOLO. For those who might not know, I'm going to introduce Dr. Maliki. Dr. Maliki is an instant professor in the computer science department at the University of Calgary. He spent his postdoctoral at the Augmented Intelligence and Precision Health Laboratory at McGill University, where he was focused on machine learning for medical image analysis. He also completed his PhD in computer science at the University of Saskatchewan, where he worked on developing methodologies to analyze genomics and proteomics data. So we are very pleased to have Dr. Maliki, and without any hesitation, I'm going to hand it over to Dr. Maliki.
Thank you, Shukra, for the introduction. I think I can share perhaps the screen. Okay, so hopefully you have my screen.
Yes, we can see the youngster. I still see Angelina is raising her hand. I was wondering if she has a question.
Yes, I have a quick question. Can I ask you?
Yeah, go ahead.
Yes.
Sorry, my microphone didn't work.
No
I have a friend and she also wants to join. Like, can she join like from today and like kind of like get into like a phase 3?
For that one, I think it might be a better idea to send an email to AI Research School with the information. And
I think she sent it, but they didn't respond to her.
Okay, so I will follow up with that. So
okay, sounds good.
Perfect.
But can she join today? So like it wouldn't. Okay.
All of the session will be recorded and available. But if you want to introduce your friend, invite your friends right now, feel free to do so. Okay, in our previous session, we actually covered classification. And for the classification, the problem is we are interested in assigning a label to the whole image. For example, this image we might say this image contains this object. We don't care about the location of that object. We don't care if there is one instance, two instances of that. So that's not of interest. What we want to say there's a cat in this image or there's a dog in this image. So that's the classification. Usually we look at this as a model that give us probability of each class. So probability of a cat being in this image, a dog being in this image. So that's how image classification works. Today we are going to talk about object detection. And also today we introduced a very user-friendly software package in Python that you can easily develop some of these models that we talk about today. Object detection. So in object detection, the problem is different from classification. We want to localize an object. And if we have several instances of them, we want to localize each of them separately. In one image, you might have only one object type, two object type, or more than that. So we don't have any specific condition to assign a single label. We don't want to say this is a cat. We might have 3 cats and 5 dogs in an image, and we want to actually localize each of them by creating a bounding box around them. And also, of course, for each of these bounding boxes, we want to say what is the object inside this bounding box. Each single bounding box represents one object. And so if you look at it, within that bounding box, we need to classify this object to see what is this, is it a cat, is it a dog, for example. So that's how object detection is different. There are a few elements to be able to build a detection model, or at least historically speaking, these elements have been used for building a object detection model. One of them is region proposal. Region means area of an image. Usually we want to take a look at a large number of regions and find those regions with object within them. Of course, we don't want to process too many regions, and also we don't want to process regions that have no information or no object in them. So there are some sophistication that could happen within the region proposal component. Similar to classification, we need to also extract some features from, let's say, from image or from different regions of image. These extracted features might actually tell us about information within that specific bounding box. Sometimes our models might give us several bounding boxes for one object. So for example, there is one cat in the image, but we have 2 or 3 bounding boxes around that cat. We are interested in the tightest and more accurate bounding box that capture the whole object. And you need a method to suppress the other ones. That's something we call non-maximum suppression. We want to apply that. And ideally, for each object, we have just a single box around it. And we need to evaluate, like every model, everything we do, we need to have some way to evaluate it to see how good this model at this point is. We use concept like precision. And of course, since we have several objects in one image, we cannot just rely on precision. We should go with average precision across those objects within an image. And also we want to see the behavior of the model, not for a single image, but across, let's say, a large number of images. This is why we have mean average precision. Perhaps you are familiar with recall, or sometimes we call it sensitivity. We talk about it as well. So we want to have this balance of recall, this interaction between recall and precision. And precision recall curve is another thing that can be used. And intersection over union is another component that I'll go through it as a evaluation metrics. Okay, we talked about bounding boxes. Here you see one example. There are 2 dogs in this image, and we have several bounding boxes. We see that some of these bounding boxes have a significant part of the dog covered, but it might miss parts. And there are a bounding box in top right corner that you see that there is no object there. We want to see how, we want to assign a score to each bounding box that's also represent what we call it objectness score. Is there the probability of an object being there? If you have a wall, a piece of a background, or here you have really a background in that one, not an object of interest. So that means perhaps we should give that box a low objective score. While a box that covers a significant portion of the dog in this image should get a higher objectiveness score. And if you still have the face of the dog, still you should get relatively higher objectiveness score compared to a box that covered the background, or a box that covered just perhaps a small portion of the body of a dog. So that's objectiveness score. Once again, we are interested in tight bounding boxes around object. That's one component. We are interested to know what is the object within this bounding box, as well as we want to assign a objectness score to each bounding box. These are three concepts that we are interested in a object detection problem. Okay, any questions so far? Let me see if I have the chat. Okay, perfect. So we talked about regions of interest or regions that might contain. I say might, yeah, because we take a look at them, we evaluate them, and we assign a score to them down the road. But we don't want to cover every possible bounding box. Remember, you have 1,000 by 1,000 for regular image size. Yeah, if you go with that, you have actually 1 million position to almost 1 million position to select one corner of this box and significant around a million to each box can be defined by 2 points. Yeah, each point can be actually defined by a million box, a million option pixel type, pixel pairs. So we don't want that to happen. We don't want to cover every possible box. We need to be selective. One approach is that has been done is the algorithm that rely on pixel values and intensity value between neighboring pixel, and that selective search algorithm. It's relatively slow. There are other approaches that rely on deep learning based approaches. So they are even the region proposal or region selection is actually is a deep learning model on its own. Okay. Bounding boxes for this image, we see that most of these bounding boxes are good candidates, but still I want one single bounding box. So this means that I need to get rid of some of them, plus I need to have a prediction for each of them. So ideally, all of these should give me a high probability for the content of the box being a dot. The goal, as I mentioned, is to get rid of all of them and pick the best bounding box here. And this is something we call it non-maximum suppression. One thing I want you to know, I don't expect you to learn all of the concept, but I want you to learn the terminology as you will be starting your work. As I mentioned, we cover a very user-friendly package that almost everyone familiar with Python should be able to actually design a model using that package for object detection. But I want you to be familiar with some of this terminology, because sometimes this terminology comes up and you have several choices for, let's say, for non-maximum suppression algorithm, or they talk about the IOU value or other metrics or measures. I want you to have an intuitive idea about what these are and how they reflect to the problem or the model that you are designing or the software that you are building. Okay. How non-maximum suppression works? There are different approaches for it, but in general, we can pick the idea is that if we have a bounding box that actually is a good representation of that image, that one should cover the object very well and should get, among others that might partially cover the object, get highest objectiveness score. If that's the case, if I get that one, I need to get rid of everything that has a substantial overlap with that, because perhaps they are redundant. How to do this? We need to assign a score to each of those bounding boxes. If two bounding box, let's say here a red bounding box has a overlap with that, I want to measure that. To do that, you can actually come up with something very simple, but intuitively meaningful: intersection over union, or IOU sometimes. So intersection of these two boxes divided by a union of this Definitely this number is something between 0 all the way to 1. 0 means that they have no overlap. 1 means that they have 100% overlap. These two are the same bounding box. So what we can do, pick one, remove everything that has a significantly high overlap with that bounding box, and repeat this process so in the next batch, we pick one, the next one with the highest score, with the highest confidence threshold, which is what we pick for the case. We know that there is a object here, high probability for being an object, and pick the one and remove everything that has a significant overlap. Well, iteratively, we do this unless we process every box. So that's the way that this could be done. It's a greedy process. Greedy in the context of software means that at each point of time, we look at the action which is optimal at the point. However, it might not be generally optimal. So through this process, there's a chance that we actually get rid of some of the meaningful bounding boxes as well, because sometimes these objects might significantly overlap. So there might be, for example, in this case, that there is just a kid, there might be two kids side by side, and both of them actually might fit in a single bounding box, and the model might count with one bounding box for two objects. Those cases are possible through this process. Remember, this is a greedy process, and greedy processes are fast, but not always optimal. There are other ways, other versions of non-maximum suppression. Sometimes we call it soft. In soft non-max suppression, we don't remove the boxes with significant overlap, but we decrease their score. That's a way to process it. There is a generalized intersection over union that actually is the IOU itself minus C minus U divided by C. Okay, what is C? C is a bounding box in this previous one, a bounding box that contain both these bounding boxes. Yeah, it should be a convex bounding box that cover both of these two bounding boxes. And C is actually the smallest bounding box that sorry, U is the area of union of two. So C, as I mentioned in the previous one, is the bounding box that cover these two, yeah? So you have two frame, you want to put it inside a tight frame that cover both of them. And C is just the union of these two, similar to this concept that we have. Definitely C minus U is, when you divide it by C, is always between 0 and 1. So what you get, it's a number in general between 0 and 1. Okay, we can also have distance-based non-maximum suppression approaches. If you saw them as a setting sometimes, that also might be the case. In this case, these approaches usually cluster boxes to different, based on some their closeness. For example, how their surface are close to each other, or the border. And then from each cluster, they pick one of them as a representative, something like that. So that's the distance-based non-maximum suppression. Okay. There are many other evaluation metrics that I think it's a good practice to know about them. Here is a Wikipedia page that include definition of different actually metrics. I don't want you to remember these or memorize them. Some of them are intuitive and make sense. You can perhaps keep track of them. For example, precision and recall. If I want to show it here, you look at this, anything within the, to give this image a context, assume that this is all of the, let's say, all of the patient that we have, we had in our database. All of them went through a test, and this test suggested anything within this circle, all of the patient within this circle suggested to be positive for a disease. So they tested these patients, and the result of the test came out positive. So this test is not always correct. Yeah, sometimes it's correct. We call it true positive. Sometimes these tests are incorrect. We call it false positive. So here you see one side of the patient. So these parts are all of the positive, means all of the people who have been sick, or the model haven't been able to identify them. We call those parts false negative. And these are healthy group. These are actually true positives, because they are true negatives. They are healthy, and the model hasn't picked them up to be, model also, or test has said these are healthy, they are not sick. So we have these four concepts: false negative, true positive, true negative, false positive. So now in this concept, when I talk about precision, I actually mean from all of those results that came out positive from the test, how many of them are actually positive? So if a test has a high precision, means that when it says something is positive, I can rely on it. However, it might still miss other parts. Recall is a little bit different. Recall means that from all of the patients who have been sick, how many of them actually been identified as sick? So from all positive patients, how many of them actually how many of them were detected by model as positive? So these two are precision and recall, are two concepts that you use it. You see it both for classification models and for as well as for object detection. If you need to think about this, read more about this, I think it might be a good read to just go through that Wikipedia page. Sometimes you need to assign a context for it, to a context that makes more sense for you. Here, for example, this could be a model that predicts a object for us. So predict being a dog. And being positive means being a dog, and not a dog is the negative. So images here are images of dogs that have been passed to the model, and model has told us, okay, this is a dog. Images are here are images of dog that model has failed to identify them as being dog. And images who are here, this might be other animal, let's say a cat, but model said it's a dog. And here is, let's say, image of a human, the model said it's not a dog. So that's, again, a little bit of context, how to bring it to the concept of deep learning and models. Any questions so far? So I have a question regarding cardinality. So here it is cardinality, but when I talk about intersection over union, here we have region, yeah? You talk about area. So have that in mind. And cardinality means size, for those of you who might not be familiar with that word. Okay, so we can have a small activity actually to what is mean average precision? So mean and average actually are the same concept. Can someone tell me what we use mean average precision in the context of object detection a lot? You see this to be a measure for different models. Feel free to unmute, or feel free to share your thoughts on the chat. So let me first talk about precision. If you compare what we had here, sorry. precision is about being positive or not positive, but we are talking about objects, a bounding box. So here is it's like in the context of classification, it makes complete sense. How we make it meaningful in the context of object. So one technique that people will use if, for example, we say this box is positive if it covers more than, let's say, 75% of the object. So if you have this box, both of these could be positive. But if you just a box cover a part of the image or 10% of it, lower than that threshold, in that case, we say this is not positive, it's negative, yeah? So in that case, actually, when we talk about mean average precision, we usually have a threshold as well. And you see that mean average precision at 50%, at 75%, at 90%. So that's the meaning of that number that you might see in when you train this model or when you use these models. So why we need both mean and average again here? So the chat is very quiet. Remember, even within a single image, we might have several bounding boxes, yeah? So the reason that we have both mean and average on precision, we say mean average precision, is that we are interested to find a measure that's first reflect different objects or even different number of objects from each type. For example, if there are five dogs or two cats, we have two objects, but from each of them, we have different number of instances as well. We want to reflect on that. Plus, we want to actually have a measure that is reflected across many objects, many images, not a single image. So mean average precision comes from that. For calculation, as I mentioned, usually you have a threshold, and based on that threshold, we will be calculating mean average precision. One approach that actually was one of the first approaches for conducting object detection with deep learning was region-based convolutional neural network, or RCNNs. So R stands for here region-based and convolutional neural network goes with CNN. So what they did is that they used a selective search, which is a heuristic approach to find, find regions of a image that might contain a object. Then for each of those regions, you can look at them, cut that region and give it to a model, a classification model, and that classification model give you, a score if this is a class, or if this is a class, what is the problem? Which object is here? So it converts this really to object detection to a classification model, because really you say you cut this box or this potential object, you pass it to the model. If it is an object, you get a higher score, and if it's background or it's not any meaningful object, it gets a low probability, as well as the class will be background class. But what is the downside here? Any idea what's the downside of this model? And remember, we might have many boxes predicted by selective search, like 1,000 or 500 or something like that. Can you guess what is the challenge using RCNN? So that's correct. Selective search is slow. That's one downside. But it has even a downside which is more significant. So one box can have many objects which cannot categorize as one suggestion. So there might be a box, that's a good point, that includes several objects, and that box still will be labeled perhaps by one object, and it's so that's caused a little bit of noise. What do you think about the speed of this approach? Do you think it's fast? It's slow? Do we need to repeat something a lot of time? So yeah, it is slow, but can you tell me why? We said that selective search is one reason, but there is another significant reason for being RCNN being very slow. So AIRS suggests that if two bounding boxes intersect, you have to run the CNN on their intersect twice. So too many bounding boxes, and really you need to, for each of them, you need to run the whole model. That's slow. Can we, instead of running a model on each bounding box, run the model on the whole image just once? So if I have 1,000, so remember this model, it's a feature extractor. From the previous session, remember feature extractor was a sequence of convolutional operators that the input to them, the image go through them layer by layer and pass through, and at the end it comes up as a tensor. Yeah, so it might be 50 layer or 100 layers, something like that. So it's a computationally demanding process, and when you need to repeat this 1,000 times for each bounding box, it's very heavy, very demanding. If we make it just a single time, that would be a huge boost. We pass the whole image through a feature extractor and then extract, instead of extract these values, because each bounding box gives me some value, yeah? Instead of extracting, instead of giving the image, this part, we can actually pass the whole image, and from the feature extracted, find out which part of these extracted features or this tensor correspond to that specific input box. So this is actually what we see. So this is the downside, as I mentioned. Again, each box should independently go through this convolution, which is a feature extractor, very slow. We can do this by doing the selective search on the original image, finding those bounding boxes on the original image, and instead of passing each box, we pass the whole image to the feature extractor. Feature extractor, usually, if you remember, those steps, either they keep the shape, spatial dimension the same, or they decrease it by 2. So at the end, I can find out which regions of this final feature are actually corresponding or is most relevant to these bounding boxes. Because I can, let's say it might be size. Let's say if we have just one downsize, this means that if the size of this 200 by 100, size of the final feature is 100 by 50. Of course, I can easily find out these coordinates in that feature space and use that. So in that case, I don't need to pass each box independently. And this is a way to save a lot of computation. So this is one more time. This is how the whole image goes through this backbone, which is feature extractor. And I know that this part of the feature is perhaps reflected to this part of the image, related to this part of the image. So I infer the features for that bounding box by picking the corresponding area on the extracted feature. So that's how I can save a lot of computation. And this is why this is exactly the same method with just those adjustments. We call it fast RCNN. Still, this method it's definitely compared to RCNN is faster. It's fast. Do you see any component still being here that is slow? And we talked about it actually. Yes, we still rely on selective search, and selective search is a very slow process. The next model that we actually talk about it is, I'll come back to the loss function, is a model that is called faster RCNN. So we had RCNN, fast RCNN, try to improve RCNN, increase the speed. Faster RCNN actually try to get rid of the selective search, that is a slow process, and change it with another component, which we call the region proposal network, which also is a deep learning model. So by making it a deep learning model, we can benefit from the speed of computation on GPU and make this process fast and end-to-end. So really the only change is the region proposal network. That's this region proposal network. What it does is that creates bounding boxes. Each bounding box requires 4 coordinates. Yeah, for each bounding box, you need 4 elements. And also, it's also assign a objectness score, probability of being object and not being object. So 2 elements for each box. If I have K box or 1,000 box, really I need a vector 1,000 of these. Yeah, so a tensor of size 1,000 of these. So this is how we work with that. So internally, what we do is that, first of all, we have an initial feature extractor. This feature extractor extracts some features. Then these extracted features will be used in 2 different ways. One version of it go to region proposal. Region proposal also is a CNN architecture, yeah? So that CNN architecture, at the end, you come up instead of, let's say, just one vector or one input, one output, or 2 output, you have K times 6 output. Yeah, this 4 is for let's say X, Y, which is usually sometimes depends on the implementation, sometimes the center, width, and height. Yeah, as well as objectiveness score. So it's similar completely to what we had for classification, with the difference is that here we have a specific number, K, for example. If we go with implementing 1,000 of these, so we get 6,000 output as a tensor. So a tensor of 6,000, for example. So now that we have this feature region proposal selected, we can do the whole process, merge this and replace the selective search completely by this one. Because remember, selective search job was to give us these boxes. So now we need to go through all of those boxes that have a high objective score. So we don't, if something is low objective, we don't need to care. And that one, this information can go directly to the classification model. If we have two class A and class B, if you have bounding box coordinates, which is something we actually have it here as well. So that's how it works. And it is fully focused on convolutional operators. Okay, so, and let's cover a few things that you might, yeah, we skipped this one. I mentioned that we have a classification module, and that's for classes, and also we have objectness score. Those are two classes that we need to keep track of it. We have a regressor that needs to adjust the coordinate of the boxes, and that one use a L1 score or to calculate. We can calculate that, and I don't expect you to go deep about these scores, this last function, because that's not the purpose, and the whole purpose actually is to provide you with the terminology that you can use object detection model in action and know the terminology. Okay. Okay. So more on region proposal. As it was mentioned, it is built on a convolutional, based on a conv networks. In the paper, they used 3x3 convolutions, means that kernel size was 3 for them, used padding wise, and number of output channel to be 5 to 512, one convolution layer. And then the output of this was actually fed to two branch. One of them was 1x1 convolution, means that kernel size is 1 here, and they create 2K output channel from that. And from the other one, the other channel, they created 1x1 convolution and 4K output channel. That way, you see that just simply based on ConvNet, a convolutional operator, they develop this network. We have a concept that we need to remember. We had X and Y to be the center of this bounding box. We need to adjust it because not all the bounding boxes are perfect. If we can push that to be a tight bounding box for that object, or we actually regress to the bounding to the object, is something that's help us to have more accurate result. And because of that, we have this component that even here, this 4K element actually give us the coordinates. So these coordinates can be adjusted, and that adjustment can happen by the next layer. So this one give me a bounding box coordinate that can be further adjusted here to give a new, more accurate, hopefully, bounding box. That's more accurate means that they result on less penalty or less loss function. One thing that I want you to know, when you provide these inputs for this model, there are different style of providing the coordinate for your model. Some go with center, height, and width. Center is obvious. Height usually for you is number of rows, and width is number of columns. You're talking about if you pass the image as a NumPy array or as a tensor. Some, instead of center, they go with that corner, and they have that corner, coordinate of that corner as a box, plus, and they have width and height for you. And some other methods, when as their input actually go with coordinate for this corner, x1, y1, as well as coordinate for this one, x1, y1. All of them are a valid approach to import your data or model your data. Depends on the package that you are using. They might have a specific expectation, and you need to transform your data to that style. So that's something I want you to have in mind. Okay, any questions so far? Okay. Remember, so there's a question on the chat. What do you mean when you say a tensor of 6,000? So each convolution layer, if you remember, we had number of output channels. Yeah, for example, this one was kernel size 3 by 3, padding 1, number of output channel 512. Here, if I say, let's say, if I go with for a thousandth, let's say, bounding box, I have kernel size of 1 by 1. Since I need 4 of them, remember, I need x, y to be the center, for example, width and height, 4 elements times 1,000. So the output channel is 1,000 here. So this give me 4,000 output channel. And this one, since it is this 4,000 actually elements here. And this one gives me, I want to have objectness score, which usually we keep track of it as two variable, and that one give me I need that to be calculated for 1,000, let's say, bounding box. So what is the kernel? So if you remember in the previous session, we see that a kernel is an area of an image that you wanna explore. Yeah. So a kernel is actually a let's say when I say a 3 by 3, assuming that the depth of the tensor is 1, really is a 3 by 3 matrix. I use that to slide it over the image, and based on at each position, I calculate the linear combination of elements that are the result of multiplication of the value for each cell and the image, the cell of the image under that a component of the kernel. So I think maybe I'll go through that one after covering this. I think this is the concept that we covered in the previous session, but in general, you can look at it as a small 3 by 3 matrix that you overlay it on a image. And when I say image in a general term, image can original image that you see as the regular things that we work with, but these images are transformed and moved to different dimension. We can call them tensor to be more accurate and more general. And based on that, each filter creates a single channel, a single output channel. So if I need to have, let's say, 4,000 channel, means that I need to have 4,000 kernel. Each of them need to be trained during this process. Yeah, so in the context of algebra, or we have a specific meaning for a kernel, but here the kernel, or sometimes called filter, refer to those, let's say, component that we need to learn from the data. And I go through one example after covering the content. Okay, so one idea comes in, and we use this, yeah. Can we, instead of, to speed up this process, can we actually go with, start with a really large number of anchor boxes and try to adjust them through deep learning model? In that case, we don't need to have, we can go with initially defined bounding boxes. We call it anchor. As we move through the network, we adjust them. And at the end, of course, we have a lot of redundancy, but we have non-maximum suppression. We can get rid of them. So let's me, yeah. This is an idea, first of all, this is an idea that we built later on it if we start with just anchor boxes. But this idea can be used to skip some of the computation here and have a very straightforward and fast implementation. We'll come back to that when I cover the result. I think I mentioned the negative and positive values based on a threshold. For example, if threshold is 0.7, we have positive means that this is actually a bounding box that covers the object reasonably well. And if it's less than something, if it's less than a threshold, we call it negative. Between those are borderline. Usually we don't penalize. We want to, penalize the model when it is very, very off. And you see that here, base anything which is between 0.3 and 0.7 in the middle is like not penalized. So in this case, little by little, I improve the predictions for those who are already correct, and I penalize those who are off to move them to toward this higher region. So this is how the training of region proposal network works, actually. Just to recap what we covered so far, we said that RCNN was a slow, fast RCNN tried to improve it by not having many, running many backbone or many feature extractor on different bounding boxes. Instead have, in fast RCNN, we have one feature extractor that go through everything, but still we suffer from a selective search. And in faster RCNN, we replace that selective search with a region proposal, which is completely deep learning based or CNN based. Okay, so how this one contribute to speed? So the RCNN one, for each image, actually, you required 50 seconds. Of course, we can't consider that to be real time, because to be real time means that you need to process at least 30 frames per second. So this is not an option. It's very slow. This, by real time, I mean that if I give you a movie, you can actually give the, play the movie back with the bounding box on it at almost at the same time. Fast RCN has a huge improvement from 50 seconds to 2 seconds per image, was very significant, but that 2 seconds is mainly wasted on selective search. Faster RCNN fixed that, significantly improved the process, but it still has 0.2, means that you can actually process 5 images per second. Still not real time. And by real time, I mean still, if I wanna do it on an image, apply this algorithm on image, there will be a lag. I can't, see the image to be processed with bounding box on the image right away. So for example, if you turn on your webcam and you want to, let's say, classify some object, that will be very glitchy, yeah, because it takes a lot of time for a single frame. We want something which is perhaps faster. How faster? This one is, we can cover, as I mentioned, 5 frames per second. We need to increase this at least 6 times faster to be able to call it real time. So there is a question on the chats. A couple of questions, actually. Is threshold value determined by the model or set by the scientist? So the threshold model, the threshold actually is something that depends on the problem, and you you use this threshold. Remember, always we go for the best bounding box, but that's something for evaluation, yeah? When we want to say what's the performance of this model. The higher this precision, this threshold is, we are more, let's say, picky about the model. If the model is off, we don't like it, yeah? If model just cover, let's say if I go a threshold of 99%, I am extremely serious about not missing more than 5% of that image. Is it important? For some application, yes. We need to have very tight bounding boxes that cover the whole object. For some applications, no. For some application, even if you, let's say you want to localize people in an image, in general, but you don't want to do any specific, there is no threat, there is no huge financial loss or concern if you miss a little bit of someone's, let's say, closing or, so for that one, 75% might be a good threshold in all of evaluation. But remember, this threshold does not contribute to the model when we evaluate it for region proposal network. For region proposal network, that's a choice, that's a hyperparameter. And that hyperparameter is something that the person who designed the model picks. And it doesn't need to be always 70% top and 30% low. It can be 70% and gets back, and you can actually increase it or decrease the 30%. So that's something that you can dynamically change. That's things that are not trained from the data and usually are set from a large number of options. We call them hyperparameter. So in that case, it's a hyperparameter. Okay. So I brought up the idea of, okay, for the rest of this session, yeah, we have enough time. We cover YOLO, which stands for you only look once. So you only look once wants to actually increase the speed and come up with a real-time object detection. Means that's using, if you turn on the webcam and build this model, that's I am hoping that many of you are able to get that one running. The process is very straightforward, actually, in the package that I give you, and I talk about it. If I, let's say, if I have that webcam on and I, at the same time, I run the model on the frame that's I get from the webcam, I should be able to create bounding box. For example, for my hand gesture, I should be able to create bounding box around my hand. And if I move my hand, you see that the bounding box smoothly come with my hand moving across the image. Yeah. So there is no glitch, and you see the movie on really in the real time. So that's the whole idea. We use anchor box that earlier I mentioned. And what is the anchor box? Is a predefined box. Is predefined, yeah. We go, for each pixel or each region, we create let's say 9 or 15 of anchor box for different region of the image, and from different aspect ratio and different sizes, because object might have different aspect ratio and different sizes. When I have a large number of these, actually this could be the base. I have a large number of them. I know that many of them are redundant, but I don't worry because I have non-maximum suppression that can get rid of many of them. Okay, so that's how I can start. And then if I have this idea, let's say this is one case. How they do it in YOLO, they divide the whole image to a S by S grid. Let's say a 16 by 16 region, and for each region they define a, let's say, 15 bounding boxes or something of that order, of different size and different aspect ratio. That's the plan is to be able to cover the whole image or object. Remember, the center of the coordinate of the bounding box can start from 1, but it can go to others. So if I have a larger size, it might be initiated, or that starting corner or corner of it might be here, but it can cover this part of the image, yeah? So as I mentioned, plus remember that down the road, we have adjustment. We can adjust these bounding boxes to make it tighter or increase them to get the whole object within them. So the whole idea is, if we go with that, we, after non-maximum suppression, we get actually the object that you are looking for in a bounding box. And this process is fast. Remember, the whole purpose, the whole idea of YOLO is to create something that is real-time, fast. There is another question regarding how would one go about determining bounds on the running time for a neural networks? It's time here, yeah. If you look at it from a time complexity point of view, really we have just a few, if you look at it, these are, depends on the size of the image, these are operations that are done, and the size, the cost for each image is the same if the size of the image is the same, yeah. However, this depends on some factors. So I can't, if I go with a factor of height and width, is not really that valuable because it's heavily it depends on many factors, including the hardware you are using. And at the end of the day, having a number, okay, this is a polynomial, doesn't help you much. Or someone might say, my image is 100 by 100, and this is constant. So yeah, technically you can call it constant, but with a large factor, yeah? So we go with how many frame per second we can process. That's a common way for images. And also this is a factor of the hardware that you are using it. So really, when you provide the speed, you should specifically say which hardware this has been processed by. However, as you go with better GPU machines, they are more expensive. For example, some of these GPU machines, you need to pay around $30 per hour of processing. So still, you want to, you can't say, okay, I have better GPUs, it's okay, I use that. No, it's very expensive. And remember, in most cases, you are doing these activities at the scale. So it's not just one image. You might have 100 customers and they might have 24/7 video created or several video created, and this might be different cameras on a company floor, or so you need to process all of them, which this means that the faster your model is, the better. You save more costs. Okay. So YOLO is actually very straightforward. By starting from that, getting rid of those extra layer, we don't need to have by actually hard coding this bounding boxes. Yes, we might lose a little bit of accuracy or performance, regarding precision, or performance regarding accuracy or other measures, but we increase the speed. And that's what they got. And the whole purpose of the YOLO model is actually increasing that. And it has done actually, there has been a lot of work on optimizing YOLO, more specifically a open source version. It's not completely open source, but it is, it is available for many activities, and not sure on commercial use. That's something I should check. Don't quote me on that, but for any non-commercial or academic or anything that you use, you can use it without any hesitation, any charge. It is on Python and available. So I assume it should be straightforward for everyone to use it. And it has been designed, it's a company designing it. Actually, the company is start based on this YOLO. They try to improve it, and they shared their pipeline with others and got traction. And now they have commercialized this algorithm. So let me go through a notebook that I can actually share with you as well. Okay. So the notebook, first of all, has been extracted from the content of the company that is open source. There are way more that you can look. I just want to show you a use case of it, how straightforward it is to use this model, to train this model. Okay, let's see. Okay, I share it through the Google Drive with you, that paper. So feel free to open that notebook. I give you a little bit of time to go through it. So do you see my screen, the notebook right now?
We see the screen, Dr. Mark.
So were you guys able to open the notebook on the Google Drive? Okay, feel free to follow along. Okay, great. As usual, a few import statement that we have, regular things. We have matplotlib for visualization. We have OS for pass, NumPy, CV2 for working with images. It's a good practice for working in Google Colab to keep track of the current folder, call it home, and instead of typing each time, you always have this home. Down the road, if you decide to move your code, then your home is different. You haven't hard coded many versions of that name, and you don't need to go through many of them. So here I have from OS, get current working directory, or CWD, give me the current working directory. And I also, I create a output directory using OS make dirs. And this output directory is within this home directory. I os.pass.join home, which is a pass, as well as the out. This way, it keep track of how to separate this. If this one has a slash as ending, and this one also has something, they don't contradict each other, and also it's safe across the platforms. And wget actually is getting a file. So here I go with one object. I download this object to the working directory. And each time you want to, in Google Notes and Colab or in General Notebook, you want to call a bash function, you start with exclamation mark. That's how it works. So if you run this, first of all, I make sure that my notebook is on GPU. Okay, GPU is correct. I run the first element, these first two. You need to download that file. It might take a little while. So now that I have that one, I go with define some constants, out directory, precision, which is number of digits that I want to show after 0 decimal points. These are constant that's you can change it based on the way that's based on your application, font color, font thickness, line type, line color, line thickness. And also I use image width because I want to, for the sake of visualization, I resize the images to a specific width. Feel free to change that. And yeah, this is a sample video that you don't need it. We don't use a video for this application. Okay, so let me run this one as well. So YOLO V8 is available through Ultralytics, which is the company providing it. It is pip installable, so that's make it very straightforward and easy for you to install it in your environments you are working, and you can import Ultralytics as well. So I just install it. Installation might take a few seconds, and it's run a bunch of checks as well to make sure that the requirements are met. To import a YOLO model, you just need to say from Ultralytics, import YOLO. And then when you have done, you can actually define a pre-trained model. So here, if YOLO V8N is a model that they are, a small model they are using, the first time you run this, it needs to download the model, which means the weights for that model will be downloaded. And if you want to learn about different methods that can be applied to this as a given object, you can use in Python, of course. You can use help and name of that object, and it gives you a long list of functionality that you have. For example, you can see that this YOLO model can have a string, and then perhaps when you create a model, you can call it on a object, and that perhaps should be in call method. They have other options like predict, for example, if you want to predict an image. And there's a source. Let's see what source is about. Source could be a string, could be integer, could be a pale image, could be a NumPy directory. So the source of the image for making predictions. Okay. Accept various type, including file path, URL, pale images, NumPy arrays. Default to set stream. I think it's also cover the numbers as well, and I talk about one number. So if you want to really this model to predict the images from your webcam, you just need to predict it with 0. We talk about that. So feel free to go through this documentation. It's a long documentation. And let's make a prediction. I just, to facilitate this and also to provide some context for you, I create a prediction and also write prediction. Prediction is just one line, you make it, really, and I want to write it in a specific path. Image inputs, once again, it could be all of those things that I mentioned. It can be image pass, or you read the image and pass it as a NumPy array. And then you have boxes. I say what boxes is, labels, confidence. Remember, boxes in the context of object detection. You should be able to guess what that one is. Can you tell me what boxes are, or what label or confidences are? Feel free to share it on the chat. When we make a prediction, it gives us bounding boxes. So we want to visualize that and overlay them on the image and visualize it. Also labels, which means that what is inside this box. Confidence is also how confident the model is. So that's the objectness score for that one. And I want this to be saved in a specific path, and names is usually the label that you get is numbers, indices, but each indices have they are assigned to a name. So that's a dictionary containing all of those names. So I go through them, some basic concept. If this one is a string, in that case, I make sure that path exists, yeah. And if doesn't exist, just is a file not found error. And I need to read the image. If there is any problem with the image, an image cannot be loaded or whatever, or cropped or whatever, I have this IO error. Otherwise, I just put the image input inside, if it is an image, yeah, inside this image variable. And if none of these things, so otherwise means if it's a NumPy array. So this method function that I wrote, it accepts only paths and NumPy arrays. Okay, if yeah, some boxes, each box should have one label and one confidence score. This means that if number of these should be equal, len of these should be equal. So I go through all of these boxes one by one. So look at this as prediction made for one image. Each box, each class ID and confidence level, they are actually synced together. The first box has the first class ID and the first confidence score. So I just really visualize this box using as a rectangle on this image. These are coordinates, and that's line color and line thickness that I talked about it. And then I want to write on top of this box the label, for example, this is a cat, as well as the confidence score, how confident I am in my prediction, to be also a label for that box. And I put this label on top of the box. A very simple visualization concept. Okay. And then what I do is really I write this image to this specific path, yeah. And this remember I had image, I wrote on top of this image, I draw these boxes as well as wrote on top of boxes some probability distribution. So that's actually, if I give one solution, one prediction for the model, it's overlay it and save it for me. Here I want, given the images, it could be one image or many image, and a model, I want the result to be saved to a specific directory. So what I do is really, if for any image in these images, I call the model, I call the model on this image, and When I have this, I get the results back. Oh, no, that was correct. So I get the result back. For each result, I create the output. I call this writing. When I wrote the file, because I want to keep track of a copy of it, I just visualize it using, I read that prediction made, and I resize it to a specific size. Remember, we went with image width, but I want to preserve aspect ratio. When I'm done with that, I can actually show it using CV2M show. Let's do this for this image, for example. We have just a single image, and that's the name of it. The model actually called. Here I have a few boxes, 81% for and 79% for person object, as well as it finds ties as well as one object. Remember, this different model might have been trained on different objects, so not all objects are there. Yeah, I think for this model they have 80 objects, and it is available through names. If you print the names, you'll see. I passed the name somewhere. Yeah, I think it is here. When I get the model, tap into it. Yeah. Yeah, so the names are actually results names. So for each of those results, there is a name, you can actually print them. We can print them. And it give you a dictionary. You see that okay, you see it for a little while and it's erase it, and the reason is that I have this clear output to clear the previous image. If you have a few images and you want to show it like a movie, frame by frame, and you want to show it. So if I move this, oops, if I want to have that, you see that 0 for person, 1 for bike, car, all the way to, I think it's 80 objects. Yeah, toothbrush, hair dryer, stuff like that, clock. So if you are looking to specifically, you are interested in just any of these, you can use the pre-trained models. But if you are looking for this model to predict something that you don't find it here, means that you need to train this model using your own data. So any questions so far? So for model training, the first step is to create your data. You need to label data. This means that you have a bunch of objects of images containing objects of interest. You go create bounding box around them. Yeah, that's those bounding boxes should be manually done. At least partially, you should be doing it manually. And then the model, I'll tell you about how to accelerate this process. This is a manual process. You can, there are different tools and software to do that manually. So you have an object, you create a bounding box for that object, and you do this for all of these images. It is a slow. It could be, if you have many objects in your images, it could be very time consuming. But for many cases, you might have a single object really. So those cases are straightforward to make it. So when you have those data created, you need to actually move it to download the data and have these bounding boxes encoded in a way that is compatible with definition that's the package of interest use here, for example, YOLO. Yeah. When you have those, interestingly enough, the process for running or training this model is, I go through the training line. It's a single line. This is YOLO task equal to detect. This is the model, the mode for training. And this is the model that you have. And this is the data that you have actually. Number of epoch, and if you want to plot the output. In one single line, you can train your model. So the challenge really is not on running it. The challenge is creating your data sets. You might need to have a large number of samples. One way to actually accelerate that, and it's a straightforward process, user-friendly as well, is to do the annotation using RoboFlow. This means that you can go, roboflow.com is a website. You can go and download your data, upload your data, and through that, it gives you some tools to facilitate the process for annotation, as well as a process for downloading. Plus, it gives you an option to accelerate this annotation, means that you don't need to train to annotate everything. You annotate part of your data. Through RoboFlow, a model can be solved, and the RoboFlow extend that annotation to others. So the downside here is that for sensitive data, you should not use. You should not upload this data to RoboFlow. Remember, RoboFlow benefits from your annotation, your manual annotation, which is fair, yeah? At the same time, it creates an interface for you to, to facilitate your work. Plus, it accelerates. It has some models behind the scene. When you annotate some images, try to learn a little bit based on those annotation, and try to annotate other images based on the model that already has trained, and also fine-tuned on this small piece for you. So that's the way to work with. RoboFlow has a pip installable Python package as well. In order to be able, when you downloaded your data, when you actually annotated your data, you can, using an API key. So here, this API key, you can't run this code because it requires an API key. That API key is a personal, for each user. There is a specific API key that you don't share it with others, yeah? So again, API key is personal information and not to be shared. You can read this, you have this API key. When you have that, you connect to RoboFlow, create an object, RoboFlow object, and you create a work from your workspace on RoboFlow. This is, I deducted this as well, because this also is a personal information. You might have several projects. You pick the name of, this is the name of that project. This is a project, and this project might have different versions. If you have just a single version of it, you can download that version for the formats that you want, and they support YOLO 8 as a format as well. Remember, YOLO is constantly changing, so sometimes you might need a little bit of cleaning and reformatting as well to make sure that your model is, your annotation is in a formats consistent. When you download your model, your data, you can train your model for a specific number of epoch, and you see that here. Mean average precision 50, for example, has been used by default for one, and mean average precision 15 to 95, which is the average of these mean average precision across. So those are reports provided. It also creates some visualization of the result that you can see and visualize based on for example, the loss functions for bounding boxes or for classes, which is helpful to give you an idea if the model still is learning. Should I continue? I trained it for 25 model epoch. Should I go further? So that's also a good thing to have. Yeah, so that's in a nutshell. What I want you actually to think of is that, first of all, as I mentioned, you can actually, instead of prediction on your images, you can actually do the prediction on your webcam. If you have, remember, if you run your code on Google Colab, it does not have access. Google Colab is a remote machine. It doesn't have a webcam. So if you want to run this on your own laptop, you need to run this code on your local machine. It's okay if you don't have a GPU. It should work for CPU as well. More specifically these days, you might need to decrease the resolution of your images if you have old laptop or something like that. Make sure to install all of the packages and dependencies, and then go through this code. The only things that really you need for prediction is when you have prediction instead of images, you need to provide a number, and that number is 0. 0 means read from a webcam. And that way you can actually train your model, predict on your webcam, which is a good way to do some, cool visualization at the same time. Okay, any other question? I think we covered and we are almost on time. Any question that you might have? And feel free to unmute as well. Okay.
So,
No question? Yeah.
yeah, it says there's no question. So thank you so much, Dr. Malaki, for this great lecture. It was really informative. And with that, I guess we are nearing to the end of the session. Before that, I just want
Shokufa, I want to add something here. Today, in almost 1 hour, we covered a topic which is it's not a straightforward topic. Please know that these concepts are not very straightforward, and I don't expect anyone being in this session to be an expert in object detection. If these skills were so easy to acquire, deep learning was not a highly in-demand skill that's many companies struggle to hire experts. I hope this session is a starting point for and actually ignite your curiosity and suggest you to or encourage you to actually go and play with these packages. As you move forward, there are courses on vision that we offer. There will be more workshops, and hopefully some of you pick projects that you might work on a vision project for object detection for the whole month of phase 3. Back to you, Shukufla, and sorry for interrupting you.
Thank you so much for this notes. And yes, I just want to add something that practice is very important. So I will encourage you to run the collab by yourself. And for that, we are holding some tutorial sessions every Tuesday at 5 p.m. So these sessions are for you to ask any questions you might have or any difficulties you might have with running the collab. So, but it is optional and it is not recorded, so feel free to join that session as well. Okay, if there is nothing, if there's not any question, we can wrap it up here. Thank you so much for staying with us, and I hope you all have a great night.
Thank you, and have a good night, everyone.